In the last two videos, we took a look at some data structures that approach data access and data retrieval in a specific way. With the stack, we had a LIFO policy, so the last thing in was the first thing removed. Then in a queue, we had a FIFO policy, the first thing in was the first thing removed. The main question that I have here is, what if we want to be able to access data really at any location? And more specifically to that, what if I want to be able to access both the front and end of a set of data using constant time-based operations? With our current approaches, and as well with our array-based approaches, we don't really have a good way of doing this. So we'll introduce a third data structure, which is known as a linked list. A linked list is basically a way of implementing an array without needing to put data inside of consecutive memory locations. The main advantage to doing this is that when we do different operations, we don't always have to rearrange or reorganize the data in memory. Because of that, we can get inserts that are faster because generally they'll only have to iterate to the location that they need to insert at, and we'll be able to work with data on both ends of the list without needing to worry about the time complexity of those particular operations. We can generally get them in constant time. There's two main approaches to this. There's a singly linked list and a doubly linked list. The singly linked list is a great introduction to the topic and mostly is going to give us some pretty good time complexities. However, there'll be some places where it doesn't work as well, which we'll see as we implement it. And the doubly linked list will give us a much more general type of setup where we can get everything close to constant time, and it will just be at the consequence of having to maintain a little bit more property inside of our node data structure. So we'll take a look at both these approaches, starting with our singly linked list. The idea of our singly linked list is going to start the same as our other data structures, right? We're going to have a node that contains a value as well as a pointer to next. And I'm going to go ahead and initialize these inside of this constructor here, just like this. Our linked list class is going to keep track of a few different things. It's going to keep track of the front, and generally I'm going to have mine keep track of the rear as well. And I'm going to keep track of the size. So these three main properties are the ones that you would usually see inside of a linked list. So starting off this idea, I'm going to show you some of the different insertions that we can do with our linked list. So what we'll do is we'll do an insert to the front, and we'll do an insert to the rear of the linked list. An insert to the front of the linked list is a pretty straightforward process, right? We'll take in a value, and what we're going to do is we're going to create a new node, which is going to have the value, and currently it's going to point to nothing. If the size of our linked list is equal to 0, what we need to do is we need to set this front equal to the rear, and they'll both be the new node that we're inserting. This is the same sort of process that we saw in our stack and queue, right? If the thing is empty, we just initialize everything to be the value that we're inserting. For the insertion to the front, basically what we'll say is, if we're inserting to the front, we're going to take our new node and we're going to make it point to the current front, then that new node becomes the front. And that's all we need to do. So the new node.next will be equal to the front. And then what happens is the front becomes the new node. And then at the end, we just increment our size by 1. So this isn't particularly anything like too crazy, right? We've seen this sort of approach many times before with our stack and with our queue. They all follow that same sort of pattern, so this shouldn't be anything too crazy. And generally, we see that this is an O of 1 time complexity because we're just manipulating data in memory. There's no sort of iteration, so it doesn't vary based on the size of the input, which is great. Insert rear is going to use something pretty similar, right? Because we have a reference to the end of the list, we basically follow the exact same process, right? We say new node is going to be equal to a node. It's going to have a value. We're going to start off with a none pointer. If the size is equal to 0, we do the same thing. The front and rear are the same as each other. It's the value that we're inserting, right? Otherwise, what we're going to do is we're going to say the value at the rear's next becomes the node that we're inserting. And then we simply move the rear node to be the new node that we've inserted. And then, of course, we're going to increment the size by 1. So here you see that there's really just subtle differences based on how we insert the node, right? With front, what we did was we set the nodes next to be the front. So it puts it basically in front of the front, and then we make it the new front. With the rear, what we're doing is we're saying the rear's next is the node that we're inserting. So we place it after the rear and then move the rear to point to our new node. That's the way that those two methods are generally working. And like I mentioned, they're both O of 1 or constant time. The final insert that we'll take a look at here is a generic insert. With the generic insert, I want to be able to insert at any location inside of my linked list. So I'll take in a value and an index. And what we're going to do is we're going to do a few checks to start off with this. First, I want to make sure that my index is not greater than the size of my linked list, because if it is, then we would be out of range. So I'm going to raise an exception on that and say index out of range. The next thing that we're going to check is if the index is equal to 0. If the index is equal to 0, I'm just going to use my insert front method. I don't want to duplicate my code. I just want to insert to the front and we'll be done. Otherwise, if the index is equal to the size, we're going to similarly call insert to rear. Because we already have that code, there's no sense in implementing it again, right? Finally, what we're going to do is we're going to insert at a particular index. So if we're not at the front, we're not at the rear, we need to get to the index that we want to insert at, and then we'll actually do that insertion. So how do we do that? Well, if you envision yourself with a couple of linked list values, suppose that we wanted to insert at this middle location too. What we would want to do is we would want to update 1 to point to the new node that we're inserting. So like for this example here, say that we were inserting the value 5 at index 1, right? What we would want to do is we want to update this pointer to point to 5, and then update 5's pointer to point to 2. We're basically going to like squeeze it into the middle of the linked list. So what we need to do is we need to get to the index. We need to keep track of what came before us and what comes next. And then we're going to place our value right between those two values that we have. So let's take a look at how that implementation is actually going to work. What I'd like to do for this is I'd like to set up a holder, which is equal to self.front. I'm going to keep track of the previous node that we saw, which will start off as none. I'm going to start I at 0. I'm going to say, well, I does not equal the index that we're trying to insert at. We're going to do the following steps. Previous is going to be equal to the current value of the holder. And then we move the holder forward by 1. And then we increment I by 1. So do you see that we're just iterating through, and basically the previous becomes what we were previously at, and then we just move the holder to its next value, right? So we're just continuing keeping track of the thing that came previous and the thing that we're currently at. Once we reach the end of this iteration, we'll be at the index that we're trying to insert at. Previous would have the value that was previous to that index, and then holder would have the value at the index itself. And what we could do here is we can create a new node, and that node will have the value that we're trying to insert, and its next will be the holder for the iteration. Then finally what we do is we say previous.next is equal to new node. So like I said before, if we were trying to get like in between two nodes, right? If I were trying to get like to this location here, right? Basically previous would be 1. So its next is going to point to the node that I'm inserting. And then the node that we're inserting points to 2. So it basically places it in between those two values, right? So that's the way that's generally working. And finally, at the end of this, all we're going to do is we're just going to increment self.size by 1. I increment it in here because these two methods already increment self.size, so I want to make sure I don't increment twice. If I put it outside of the else statement, we would end up incrementing the size twice in some cases, which we want to avoid doing. So that's generally our code for a general insert. So there's a few interesting cases for this. You know, the best case is generally going to be an insert to the front or to the rear, where it would be constant time. The worst case would be ON, right, where you have to iterate essentially the whole linked list to get to the index that we're looking for. But in most cases, this actually iterates faster than that. It's going to iterate just the number of times it needs to get to a particular index. So because we don't need any reorganization of memory, this is actually a bit more efficient than the array or list-based approach that Python provides to us. So this gives us a bit of efficiency. So what I'm going to do is I'm going to show you just that these methods are working, and then what we'll do in the next video is we'll implement our deletion methods, which is the next set of values that we might want for this. So again, this is O of n for our time complexity. Let's just try these out and see that everything's working. So I'm going to create a new linked list, and I'm going to do an insert at the front of the value 1, I'll do an insert at the rear of value 2. And then I'm going to insert the value 3 at index 1. And I'll just do the same thing again, right? I'll just insert the value, say, 4 at index 1, right? The one question I have here is, how do I actually print out these values? So maybe we want to create like a print method is sometimes nice to have. So let me create a print method here quickly for us. The idea of the print method is an iteration. So I set holder equal to self.front. And then what I do is I say while holder, we could say holder.next. I'm going to print holder, and I'm going to do holder equals holder.next. This essentially is just going to iterate through our linked list starting at the front, printing the value each time. I'll do holder.value here to make sure it actually prints. And that should give us a good print, so we'll go ahead and call that to print out our list. Let's run this code and see what happens. I'll do a Python 3 of chapter 5 node.py. And you'll see here, this ended 1 early, so sorry, that should just be while holder. There we go. So do you see here that 1 got inserted to the front, 2 got inserted to the rear, and the values 3 and 4 both got inserted at index 1. Basically, the first index placed it here, and then the next time we inserted 4, it got placed at index 1, so it ends up as the values index 1, and 3 ends up pushed back to index 2. So we can see that this generally does look to work quite well for us, and we can see that the time complexities for this are generally pretty good for a general type of insertion. So what we'll do in the next video is we'll take a look at the ways that we can delete values from this list to see how we can delete front, delete rear, and then delete at a general index as well. So thanks so much for watching this video, and I'll see you in the next one.